right, let's look at the introduction to the precise definition of a limit. I always give the example of my husband will make potatoes out of a box, instant potatoes, right? And so when you measure the water, it's 2 cups, okay, for 1 serving. And I always find it funny because he'll get right there, try to get exactly 2 cups. Well, you're never going to get exactly 2 cups, right? You might be a little bit over or a little bit under. Well, is that a big deal? Well, it might be if you're too much over because you might have runny potatoes, right? Or if you're too much under, you might have dry potatoes and have to add butter or something like that. So let's look at a measuring cup. And have you ever wondered why these stripes on a 1 liter measuring cup, all right, we're going to go metric on you, are about 1 millimeter apart? So if I have a 1 liter measuring cup, and this is a right circular cylinder with a radius, so that's half of all the way across, of 6 centimeters, I know that the volume of a liquid that I put into this cup is a function to the level, okay, the height, my level h, which is my formula volume equals pi times the radius squared times the height. So I said that the radius was 6 centimeters, so I could plug that in. 6 squared, 6 times 6 gives me my 36, and I have this formula now that I want to keep within a certain area. So let's talk about that. How closely must we measure h, that height, to measure out 1 liter of water? In other words, 1,000 cubic centimeters, with an error of no more than 1%. So that's my error. As long as I'm with 1%, I'm happy with my potatoes. So my 1% then would be 10 cubic centimeters. So in other words, we want to know in what interval to hold values of h, that height there, that satisfies this inequality. Okay, so in other words, my volume that I said minus this 1,000 cubic centimeters, I want to hold it within 10 cubic centimeters because that'll only be a 10% error. Well, I know what V is, my volume. We just found that, so I plug that in. How do we solve an inequality? We get rid of these absolute values and we do the plus and minus. So notice I have a negative 10, positive 10. I want to isolate h because that's the interval that I want, is that height there. So I could add 1,000 to all 3 pieces. I could now divide by 36 pi. And what this gives me is it gives me this interval to keep h between. Now it would make sense that if I'm a little bit below to round this one up, if I'm a little bit above to round this one down, because it would shrink even our interval even closer together. So basically this just says we should hold the interval, this 8.9 minus 8.8, which gives us 0.1 centimeters wide. Guess what? That's 1 millimeter, which is the reason that your measuring cups have about 1 millimeter apart, because this gives a 1% accuracy, which is more than enough in cooking. So that's what we've been talking about. It depends on, well, how small do you make your interval? Well, it depends on what you're doing. Is a 1% accuracy in cooking good enough? Well, maybe if you're a, big time chef, maybe not. But in this case, we think it's just fine. All right, so here is our definition. It says, let f of x be defined on an open interval about x naught, except possibly x naught itself. Remember I told you you cannot read math like you're reading English. Break it apart a piece at a time. This is saying I have some function. Let's get another color here. And so what does my function look like? I don't know. But then I have some open interval, let's call it within this interval, about an interested point, and we call that x naught. Except possibly x naught itself. Well, what does that mean? Well, we said last time there could be a hole there, right? The limit still exists because as I'm approaching the limit of my f of x, as I'm getting really close to x naught from either side, I am approaching this value, and that's what we called the limit. Okay, that was that definition. Well, we're going to add this piece here below that says, well, what if I'm interested in an error? Remember my measuring cup that I said, well, I want to keep within a 10% error, and so I know I'm not going to get exactly that limit, but I could be a little high and I could be a little low, like my measuring cup, and this is what we're calling this epsilon. Epsilon's going to be greater than 0, right? Because you're going to have some error. It's going to happen. So I'm going to have some limit plus epsilon a little high and a limit minus epsilon a little low. So that's all this is saying, is I have a function, think of the volume of the measuring cup, minus some value, that height that I'm trying to stay within, and I want to keep within some error, again my 10%. Well, wouldn't it make sense if I'm trying to keep my limit, my y values, contained, then if I look straight down, my x values are going to be contained as well, and that's this piece right here. All this piece is saying is that this delta, I want this distance here, we'll call it plus and minus delta, to be centered around x naught. And this will make more sense when we get, more into some exact examples. So that's what this says here. Make epsilon as small as we want, and we could find the new interval. Okay, so this becomes my new interval, epsilon, closing in on this limit. So in other words, x naught's what I'm interested in. I'm approaching it, getting as close to it as I can. So in other words, my function is within here. I'm trying to get as close to it as I can because I want to keep a particular error. So in other words, the value of delta, my input, is going to depend on my output, how much error that I'm going to have. You always begin with an epsilon greater than 0. That makes sense. We keep saying you're going to have some error. It's going to happen. So always begin with some error that you can stand, and then determine an appropriate input so you stay within that error. You must ensure that the function is defined at some interval around x naught. So the function must be defined, can't be any jumps or anything. But again, we said not necessarily at x naught, because there could be a hole in the function. Because remember, we said the limit does not care what is happening at the point, but only around the point. So this definition doesn't tell us how to find a limit, but it shows you how to verify a limit is correct. So the bottom line is we need to know what input value of x will result in an output value of f of x that are near a particular target. And that's this error, this epsilon. So basically what we do is we're watching the value of the function as x approaches x naught. So as I'm getting close to this x naught, and let's say I want to stay within 1/10 of a unit from the limit, L, as x stays within some distance delta. So what I'm looking at here, and again might be easier to see with an actual drawing of a graph, is I have some function and I want to keep my error within 1/10. So guess what? That means that if I want to stay within that error, then I also need an input that's going to keep me within that error. And what I can do with this is I can say, well, each time I need a new delta, remember that's my x, you could think of your error, your interval around your x naught. As I keep picking new tolerance, my error tolerance, then this is going to change. My x values will change because I want to always keep it centered Think about why you want it centered. You want the smallest possible interval around your x. The skeptic versus the scholar. The skeptic presents an error, an epsilon, challenges to prove the limit does not exist or we have room for doubt. The scholar says, I don't care whatever epsilon error you want. I guarantee you I can input a value around x naught that keeps x close enough to x naught to keep my function within a desired tolerance. So in other words, they make a challenge and they say, well, I bet you can't keep, I know you can't hit that limit exactly, and this is around x naught. I bet if I have this function, you can't keep my error within plus and minus 1/10. Okay, so that's basically what the skeptic says. And the scholar says, oh, yes, I can. I can put an input around this plus and minus delta to ensure that I stay within that error. Well, then the skeptic comes back and says, okay, how about make the error smaller? I bet you can't do it now. Well, certainly. Notice what's going to happen is my interval around x naught is going to get smaller. So notice on the left, this is keeping my function within this limit, within a particular error. And we're just going to make the error smaller and smaller. And then our scholar comes back and says, I can always center around this x naught some inputs that will make my output stay within that error. And we can continue to do this. If you notice what's happening, the error around my limit's getting smaller and smaller. Well, guess what? My input's getting smaller and smaller until we get to a point where we say, I don't care how small you want your error. I can always, if you want your output to be within these values, I can always center it around this x naught, my input, that will ensure I stay within a plus or minus delta in here that will keep me to make sure you have no more than that error you're looking for in your function. Let's go back to our definition. So we were good the first part, right? Because that's what we've talked about, of finding limits as x approaches some particular x value, x sub naught. Well, we typically do this right side because this left side is going to imply, meaning that the skeptic, I say, I want to stay within a certain tolerance, okay, whatever my desired precision is. And then to do that, I'm going to stay with my delta plus or minus my x values. Okay, that's going to be my x values, and I'm going to center them around this x naught. So let's look at centering intervals first. So if I want to center an interval around a point, okay, so I'm looking at centering an interval around a point on the x-axis with the point x naught inside. So I'm just looking at an x number line right now. Then find a value of delta that's greater than 0. So this is going to be my interval around my x naught, such that for all x, I keep within this interval. Of course, my interval around my x is going to be greater than 0 because I can't get perfect. And I'm going to stay below this delta that will be the smallest, that will make my interval the smallest. So let's see how we could do something like this. So let's say that I have a equals 1, b equals 7, and x naught equals 5. All right, what this means, if I have a number line here, and of course I have 0, 1, 2, 3, 4, 5, which is what I want to center it around. And so there was my A. And then 6, 7, there's my B. And what I want to do is I want to center, I want to have an interval that centers around x naught. Well, if you're kind of using your noggins, you can say, well, that's easy because the smallest interval would have to be, it would keep this 7, so that would be 2, and I'd go 2 below, and that would center it around 5, where these two values are plus or minus my delta. Well, let's actually see how to do this with my precise definition of a limit. So that is my 0 less than the absolute value of x minus x naught, absolute value less than delta. What this means is I want to center around x naught. So let's go ahead and plug x naught in, which is 5. And then to solve this inequality, I would do the plus or minus delta. Absolute values go away. And at this point, to solve for x in the middle, what I'm going to end up with is a 5 minus delta and a 5 plus delta. Okay, so what does that mean? This lower one, the 5 minus delta, I set equal to my lower value. The 5 plus delta, I set equal to my upper value. Now I can solve this. So if I solve this for delta, probably the easiest thing to do is chunk the delta to that side to make it positive and then subtract 1. So I get delta equals 4. In this case, I just chunk the 5 to the other side. 7 minus 5, I get delta equals 2. So therefore, the value of delta, which assures x minus 5 stays within this delta, and it's centered between this 1 and 7, is the smallest value, which in this case is my delta equals 2. So that's how I ended up getting this 2. And you might say, well, that's silly. That's a whole bunch of stinking work. Just when I could look at it, you're going to see later you can't just look at them. So realize the key here is to realize this step. When you're doing this step right here, what you're doing is you're centering around your x naught. Okay, back to our definition. It is very important that you understand these two pieces, okay, are the definition, in this case, of our limit. Where this piece, the right-hand side, says we have a function, we want to stay within this limit within an error. It's the best way to think about it. If I stay my output, my function's my output, then my input needs to stay within a certain centered, and that's what we're doing this step, we're centering it. I need to stay within this interval. So once again, if you think of your output being your mashed potatoes, and you want to keep your mashed potatoes within a 1% error, then let's center it around how much water I'm going to put in to ensure that you keep within your error and you're happy eating your potatoes. Let's find the deltas algebraically with this precise definition of a limit. So what I'm going to do is say I'm going to give you a function f of x equals the square root of x plus 1, where my limit equals 1. My x naught, my input, I'm going to end up centering this around is 0. And my error, my epsilon, is 0.1. So by the definition, if we do this in 2 steps, the first step is my f of x minus my limit less than epsilon. So this is going to be when I keep my delta centered around this x naught. And we'll get to that part. So what I want to do right now is I want to take and get another color, and I want to plug in my function. I plug in my limit, and I plug in epsilon, and that will give me my inequality that I can solve. So absolute value square root of x plus 1 minus 1, absolute value, less than 0.1. Well, we got this inequality absolute value stuff down, right? The negative less than, get rid of the absolute value, x plus 1 minus 1, and then the positive. Probably what I would do is add 1 to all pieces, because I'm trying to get x by itself in the middle. So I get 0.9 less than square root of x plus 1 less than 1.1. Well, if you have a square root, if you square all the pieces, you get rid of the square root. So 0.9 squared would be 0.81. When I squared the square root, that's hard to say, try to say that 5 times fast, that cancels out, so I end up with the square root being gone. And then 1.1 squared is 1.21. Well, one last step, let's subtract 1 from each piece. And I get negative 0.19 and 0.21. So this is saying that to stay within that error, this is the interval, I need to keep my x. Well, the second part of the definition says, well, wouldn't it make sense to center it to get the smallest interval? And that's what we did the last example, was how to center it to get the smallest interval. So let's do it. Let's center it. So, let's get crazy and get another color. So then step 2, I'm going to use this piece, the x minus x naught, and of course it needs to be greater than 0 and less than this delta. Well, if you go back to the previous slide, I said that x naught equals 0. So I got no problem with plugging in a 0 right there. And now I do the plus or minus. So I'm going to have a minus delta less than x less than delta. So this says my minus delta must equal my lower value, which on the last slide was negative 0.19, or solving for delta would be 0.19, just divided by negative 1, however you want to say it, made both of them positive. And I had another one, I had an upper delta at 0.21, and we always pick the smaller one. So this would be how I'm going to center. My interval is going to be around plus and minus 0.19. All right, now that's all lovely and everything, but I'm sitting here and looking at all this chicken scratch and saying, I don't know what you're doing. If you would draw this out on a graph, I think it will help. So what we're doing here is we're saying, so notice this is my x naught right here. We said x naught 0, and I want to center within an interval that I can input a value that's going to keep my limit, okay, that's going to keep my limit within, remember we said my limit was 1. The first part I said, well, that's fine, okay, if I'm looking at my error 0.1, well, 1 plus 0.1 would be 1.1, 1 minus 0.1 would be 0.9. So as long as I can stay within this area right here, my output, then I'm happy, right? Because that keeps me within my error of my limit. So we did that. The first part, we said, well, that's great as long as you're between negative 0.19, and if you remember, the high part was 0.21, and so we're happy. The second part said, well, hey, why not center it around the smaller delta? And so that's where we ended up centering it around this 0.19. So it really helps to graph this. So what did I graph? I graphed my function. I graphed my, well, I guess I didn't, but I knew my limit line was at 1, so I'm a liar. I meant to graph 1, so that's my interested, but I can see really my interested area is between the blue and the green line, okay, between my f of x equals 1.1 and f of x equals 0.9, because that keeps me within 0.1. And to do that, if I stay within my input here, centered around x naught, I'm as happy as can be. Well, besides finding the deltas algebraically, what else can this definition be used for? Remember that I said that this definition does not tell you what the limit is. What it tells you is there's a way actually to prove the limit. So let's try this and see. So I want to prove that the limit of 5x minus, that's supposed to be a 3 equals 17 as x approaches 4. Right? Well, if I just plug in 4, 5 times 4 is 20, 20 minus 3 is 17, looks good to me, but that's not a proof. So if I want to prove this, then what I'm doing is I'm letting my epsilon be greater than 0, because I know there's going to be some error, okay, within that plus or minus. And so then according to the definition then, we must find our delta, our input error, it's going to be greater than 0, such that my f of x, which is 5x minus 3, minus my limit, 17, absolute value, is going to be less than some error. All right, so that's my f of x minus L less than epsilon. And we're going to say this is going to happen whenever my 0 less than x minus 4 less than delta. Where'd that 4 come from? That's my x naught. Okay, so that's as my x approaches x naught. Well, to do this, we do the same thing that we've been doing. We take this piece right here. I do the plus or minus, so I'm going to have a negative epsilon. Inside here, let's go ahead and say negative 3 plus negative 17 is negative 20. And then I have a positive epsilon. Then probably what I would do is add 20 to all pieces. So that cancels out the 20 there. 20 plus epsilon. And then finally, I would isolate the x by dividing every piece by 5. So if I wanted to make this look a little better, it's 4 minus epsilon over 5, and then 4 plus epsilon over 5. So notice what's happened here is if we choose, so if we choose our delta to equal whatever we want our error to be over 5, notice that's these pieces right here. So no matter what epsilon equals, as long as it's greater than 0, we will always have a corresponding delta. as long as we choose it to be epsilon over 5. So in other words, let's say, for example, well, what do you want your error to be? I don't know. I want my error to be 0.1. Well, then guess what? I choose a delta of 0.1 over 5, and I'm happy. So in other words, this would be plus and minus. I would be centering around my x naught, a minus 0.02 and a plus 0.02, and as long as I did that, that would keep me within my error of my function, of my plus and minus. So what we've seen here is how to find algebraically a delta for a given function, limit, x naught, and error, epsilon greater than 0. So the process of finding this delta, we actually plug everything into the f of x minus L less than epsilon, and we solve this inequality, which will give me my open interval containing x naught. Okay, and once again, remember, it doesn't have to equal x naught. And then the second part is I use this inequality. I find a value of delta greater than 0 that places this open interval centered, right? So that's important that you understand what are you doing here. Is I have some function, once again, and I want to know to stay within a certain limit, where would I find an interval to hold? Okay, so here's my limit plus my error, my limit minus my error. Where would I input my interval to input values? That's that piece. If I want to center it, meaning notice this one's a little far apart and I want to get it centered, then that's my second piece. How do you learn this stuff? Examples, examples, examples. You got to practice. So let's practice. For the given function, square root of 1 minus 4x, the point x naught is what I'm trying to center it around. I have some error that I want to keep my limit within. Find this limit, then find a number delta greater than 0 such that for all x, I'm staying within this interval. I'm going to find my interval for x, my inputs, and then I'm going to center it. So away I go. Step 1, absolute value f of x minus L less than epsilon. I have f of x, I ruh-roh, what's L? How do I find, what do I do? They didn't give me L, I don't know what to do. Sure you do, you know how to find a limit, right? So my x naught is -6, so this says find the limit of the square root of 1 minus 4x as x approaches -6. Easy peasy, right? You simply plug in -6, I get negative times a negative, positive, square root of 25, I get 5. So sometimes they won't give you the limit. In other words, you have to find that first. So this is why for a while I would write the formula down over and over and over, or I should say the definition. That way you're just plugging things in, and when you get to something that you don't have, you know you need to solve for it. All right, so now I got all my pieces. So I plug in my function minus my limit less than epsilon. All right, what do I do next? I want to do my negative, my positive, get rid of my absolute value. And now next, I probably would add 5 to get rid of this -5 in the middle. So I'm adding 5 to all three pieces. And so I get 4.3, these 5's canceled, and I get 5.7. Continuing right along, I probably would take square roots of every single piece next. After I square root, I get 18.49. The square root and the square canceled. I said square root, I'm squaring, you know what I mean. So I square everything. I probably would chunk this 1 out of here. So I'd subtract 1 on every piece. So in the middle here, I have negative 4x. I subtracted 1, subtracted 1. It's all good, no problem. This is algebra, right? And so now I would divide every piece by negative 4x. You remember what you do when you divide inequalities by a negative? You remembered that, right? I know you remembered that because you wouldn't let me down. Don't forget to flip the inequality signs. This algebra is just going to come back to haunt you, right? And so now I get my nice little calculator out. And I don't know about you, but this kind of creeps me out seeing inequalities written this way because I know negative 7 is smaller. So what I end up doing is just flipping these around. Okay, and I just do that because it's more natural to me to see the smaller number on the left. So again, what does this mean? This means that my x naught, my first part, what I did is I found the interval to keep my x naught in, and that'll keep me within my error. And so I can pretty much see here, I can really just look at this and see what's the smaller one. And so I can convert this by centering it into the smaller one. And that's what you're doing in this step. So let's, just for sake of, I didn't want to just stare at it here and figure it out on my own. Let's center it with this piece here. So my x naught, negative 6. I do my plus and minus delta. My animations are getting crazy. So I subtracted 6 from all 3 pieces, so it got rid of it there. And then remember, after you get this piece, you set it the lower. Remember, this was our lower. You set the lower equal to the lower on the step above. You set the upper equal to it, and you pick the smaller one. So see, you can see why it makes sense why you're picking the smaller one, because you're going to get a smaller interval here. Let's look at an application. Ohm's law for electrical circuits, like this one shown, states that V equals Ri. R times I, where V is constant voltage, I is the current, and R is the resistance. Your firm has been asked to supply the resistors for a circuit in which this constant voltage will be 120 volts, and the current is to be 5 plus or minus, looks like something to do with a limit that I got to stay within an error, plus and minus 0.1 amp. In what interval do I have to keep my resistance so I stay within this error? So I'm basically looking at all of these pieces. I'm taking my original equation here, okay, and I want to be able to figure out this interval, okay? So in other words, my I is what's going to be my plus or minus my error. But let's look at all these pieces. If I plug in my f of x, in this case, is I'm concerned about the I, okay, so that's the big part that I'm concerned around, and I want to keep this is like my x naught value, but my limit in this case, I want to keep this limit. I would love it to be at 5 amps. Ain't gonna happen. You're not gonna get it exactly 5, so I would like to keep it within this error of 0.1 amp. So away I go. I just solve this like normal, because as you can see, I have this solved. In this case, all I care is it says at what interval does R. So my equation needs to be in terms of just R. I take this, I add 5 to all 3 pieces. Now I do kind of a crazy thing where I can flip these, but remember, when you do that, you're flipping the signs as well. So I'm 4.9 over 1, reciprocal. Flipping that one, flipping that one. And then I'm just, again, I mentioned this before, more comfortable with the smaller one on the left. So that's all I did here. And now finally, to get r by itself, I'm going to multiply all three pieces by 120. And this gives me, in this case, what I have to keep my resistance in between. And I can certainly look at this on a graph. I can see my limit. Okay, and going back here, 23.53 and 24.59, as long as I stay within that limit and I plug in these values of resistance, that makes me happy. That'll keep me there.